All right, let's see what we've got going on here with this lesson 7-2. We are going to talk about angles in the unit circle. We're actually getting into some real stuff here with some radians and radian measures, and that's just another way of measuring angles. So let's take a look and see how we're going to do it. It's going to use the unit circle, terminal side where we start and stop. Here's the two big ideas. So we've got the idea that we're going to start here on the x-axis. That's always our initial side where we start out here. And if we're rotating in a positive, it's counterclockwise, and wherever we stop for that angle measurement, it's called the terminal side. We can also rotate in a negative direction, and because they stop, and you can, in addition to all that, you can even go around more than once and end in that spot, for why they refer to it as the terminal side. Then down here, we're going to have these things called radians, and that's a new way to measure angles. And here's the main ways that they compare to degrees. So let's get right into it. First thing, again, just said it, initial side, terminal side, we can do positive, negative rotations, and we can do more than one rotation to end up in the same spot. So just a reminder, we're going to need this idea. We did this in one of the last lessons. If we have a 30, 60, 90 triangle, that whatever this shortest leg is, the hypotenuse is double that. And if you remember how we did that, if we had another 30, 60, 90 over here, we'd have 60, 60, 60, and these would all be the same. So if this is 2x on the hypotenuse, if it was equal, this would be 2x, so we cut it in half right here. Now we did Pythagorean theorem to find out the long leg was always x times the square root of 3. So sometimes when I do this, I just remember it just because it kind of sounds good. The x is because it could be any length, but if I just as a basic triangle, I go 1, 2, square root of 3, and then if you stick the x on each one of those, you've got it. We did the same thing with 45, 45. We got our two 45-degree angles. From geometry, hopefully you remembered that meant those legs were always going to be congruent. So if these were x's, did Pythagorean theorem, hypotenuse was always x times the square root of 2. And in somewhat of a similar fashion, I remember that one with 1 square root of 2. All right, so let's get on to an actual problem. That's just to hopefully review for you. So they ask us what's the measure of this angle. They're talking about this angle right down here. And obviously it's over 90. If we come over here, this triangle, if I draw it in here, right there, that's going to be the x right here is 4, and the y right here is 4 square root of 3. And if you notice the 4 and the square root of 3, that means that this, if we were to have taken a look back here again, that we've got like this x and the x squared root of 3. So that means the hypotenuse, if we needed it, would be double, and that it's a 30, 60, 90 triangle. So this is really 8, and then that means this is 60, and this is 30 from our other relationship. So then this is 30 in here plus this 90 right here, which means this angle, that angle right there, is 90 plus 30, or 120 degrees. So that's how you can use your 30, 60, 90 to find it. And then we're going to always know that you could have a negative rotation. So if this was 120, we need another 240 to make a full 360, this 120 right here. But when you go clockwise, that's a negative measurement. And if you went around more than once, like we're showing over here, you've got a 360 plus that 120 that's right in here. So that's where they got the 480 right here. And then because all these angles stop at the same place, they're going to have the same, what's called a reference triangle in here, that 4, 4, and 4 square root of 3, and the 8 square root of 3, or the 8 at that spot. So that's vocabulary. Moving over here to the first, on example 2a. if I've got the 130-degree angle, what is the reference angle? That means if you drew this triangle in right here on the other side, it's always the reference triangle is always made and the reference angle with the x-axis. So if that's 130, this is 50 is the reference angle, the angle with the x-axis. 90, and then this obviously would be 40, but the angle we'd really be working with is the 50. What's the reference angle over here on this one? So 210, there's 180 used up to there, right? And 180 makes 30 to 210. So my reference triangle would sit right here, 30, 60, 90. So the reference angle there is the 30. And one more. So if you got a 45 right here, that is my reference angle right there. And they want to know what's the terminal side. And so if you were doing the 45-degree right here, if you were coming around right there, what's the a reference angle is 45, and its terminal side is in quadrant 4. That are just describing. Remember, if you're doing your quadrants, how those get labeled. 1, 2, 3, 4. I always remember a student told me once that it was like making a letter C. As long as you do your C from the top down and go around the origin, that's the order they're in. What are the positive measures and negative measures of the angle? Well, the negative measurement is the 45 because that's this one right here. So my negative is a negative 45 degrees. Well, how much do I need going around the other way? Because these two angles, if you disregard the negative, positive, are going to always end up being 360. So what's left there, I believe it's 315. If you added 315 and 45 degrees together. So this all the way around here is a 315 degree angle plus the 45 makes 360. All right, next idea that comes into play here, the unit circle has its center at the origin and a radius of 1. The unit circle, unit being the key word. Why unit? Because radius, 1 unit. So it's formed where you have 1, 0, 1, negative 1, 0, and 0, negative 1 on the axes. And then one of the things, so they say that the sine always is y, cosine is always x. And why did they say that? Because if you're doing sine, for example, so opposite over hypotenuse, what's the opposite side from this angle? The y. Over what's the hypotenuse can always be a 1. So sine is y over 1, or we're going to get used to eventually if you work with enough trig, associating sine always with the y, and cosine being ka, just kind of the correlation to that would be the adjacent side over the hypotenuse, x over 1. So cosine is always going to be the adjacent to the angle, and it doesn't matter where you draw your reference angle, adjacent is always the x side, and opposite is always going to be the y side, no matter where you draw it. You got your adjacent x and you got your opposite y, the opposite being away. So cosine is always going to be x over 1, or get used to you thinking it as the x. So in the circle we have here, if we have a measure of 60 degrees, so remember 60 degrees, that's going to be like sitting in there like that. Just like they're showing right here. I'm just going to redraw it so I have bigger space to work. And the terminal side, so remember what we said, if this is 1, that means this is going to be a half because the short leg's always half of that. And then this is a half times 1, 1, 2, and then times the square root of 3. So you got a half square root of 3, which is also going to be known as square root of 3 over 2. So what are the values of x and the y? The x, 1/2, so that's like the cosine, it's going to be the cosine of 60 is 1/2. And then over here, the y side, this is like the y, the vertical, And right up here, you could do these coordinates right now too. They'd be 1/2 on the x, 1/2 on the x when you go right there. And then when you go up on this side. So whenever we're talking about the unit circle, works really nice to find these numbers. There's a square root of 3/2 for the y. So this is going to be like your sine of 60 degrees, your reference angle. So answer to the question though, the x was the 1/2 and the y was the square root of 3/2. So if in class we would actually do this, where I'm going to actually pull out a cylinder, say like it's a tube of, I don't know, wet wipes or something. So you've got your cylinder. And then you've got a radius on the cylinder. And if you take a piece of tape and make it this length of this radius, and then you wrap that tape all the way around the cylinder and then stretch it out on a desk and lay your tape out here, that would be the circumference here. Circumference is 2 pi r. And if I asked you this question, how many radii does it take to go around there then? So you measure off the radii on here, and it should come out to actually just 3 and a little more. And here's the idea. So if 2 times 2 pi, circumference is 2 pi r, that's how long this is, 2 pi r. And 2 pi r, multiplication is just repeated addition. So how many r's are there right here? Well, there's 2 pi of the r's. If you're like, well, what are you talking about? I'd say, well, if I told you I had 3 plus 3 plus 3, that's the same as, let's put one more in there. That's 3 times 4, right? 4 3s added up. Well, that's what we're doing here. How many of these r's do we have here? Well, we have 2 pi of the r's, because 2 pi times in multiplication is how many of them are added up. So there's going to be a little bit more left over there. So we're going to get used to that eventually, that how many radians are there around a circle? There's 2 pi of them. And that's what we're going to end up using when we get into this next thing, when we actually work with it here. So what is the radian measure? The radian measure of a central angle. So this angle right here is the length of the arc on the circle. So if I said to you, if you took this radius right here, or this one, and you stretch that out on the circle right here, since this is 1 unit, this is 1 unit, and the angle formed here at this point, this is going to be a radian, 1 radian. So 1 radius angle, 1 angle formed by a radius on the circle is a radian. An angle that measures 1 radian subtends an arc on the unit circle with length 1. So this only for the unit circle. For the unit circle, this is what we're talking about, because we have a radius of 1 here. So if you go 1, whatever it would be, if you go 1 of these on the circle. Same as what I was describing on the last page when I said get a cylinder and actually measure it out and put the tape out. How many radii are there? Should be 3 and a little more, 3.14, or specifically pi. So the radius of the unit circle is 1. Circumference, and this is what they're showing you here. Circumference is 2 pi r, but we already said on the unit circle we have a 1. So we have 2 of the pi's when you go around it. So that'd be 6.28-ish. So if you went around here, a radius, since this is 1, that's 1, that's a radius. If you went all the way around, there's 1, and there's 1, and there's 1, and you keep going like that, you're going to have 6 plus a little bit more extra left over. All right, so if we keep going, how many radii are on the arc? Again, if you take the arc's length, so this length all the way around here, and you divide it by the radius, that's going to be how many radii are around there, which is the length of an arc in radian, or theta if it's radians, can be calculated by taking the length of an arc divided by the radius. So how can you use a radian measure to sketch an angle? So suppose we have 4 pi over 3. So if it was 2 pi all the way around the circle, okay, halfway around is going to be pi, and then if you split each of those in half, and now we've got 4 pi over 3, so we got to split things into thirds. So if this is a whole pi, a third pi over 3 to here, and then a pi over 3 here, so 2 pi over 3, and then 3 pi over 3 right here would be the same as this whole pi. And so a 4 pi over 3 is going to be right down there, right here. And each of those, because a third of this pi, or this is going to be like a 60 degree in here, because they're going to have a 60 there. You can have a 120 over here, and then that'll take you, this right here should have been up here. And then your last one there would be your 180 there. And then you could keep going following that same pattern. So if the circumference is 2 pi r, there are 2 pi r's around the circle. This, I kind of talked about this earlier on that one example a little bit. So there's 2 pi of the r's. And then that means all the way around the circle, 2 pi radians, all the way around the circle in degrees. If you divide both sides by the 2, you can also have a pi radian equal 180 as kind of your conversion factor, if you will. Example 5, convert between degrees and radians then. So again, I'm going to use the 180 degrees equals pi radians as my conversion factor. And so if I wanted to do, let's say that I had a degrees, let's say I had a 50 degrees. And I'm just going to use the stoichiometry conversion. If I want to get rid of degrees, I'll put it down here. If I want to end up in radians. So hopefully you've done this in science before, so you understand that degrees divided by degrees, those labels can cancel out, and I'm left with, let's see, if I divide by 10, that would be 5 pi over 18 radians. But it's all based off from using this as a conversion factor. You could use the 360 equals 2 pi radians, but if you do that, then you still have to simplify later anyway to simplify it down to the pi and the 180. So B, so let's use a couple of specifics. I've got pi over 7 radians. This radians is like it's in the numerator up there. If I want to get rid of radians, end up in degrees. We said pi radians is 180 degrees. And so there's, again, put the radians here because I want to end up in degrees when I'm done. And the pi over pi would simplify, and I'd have 180 divided by 7, whatever that is, degrees. On the second part, if I have 75 degrees and I want to end up in radians, I'll put my degrees down here, 180 degrees, and we said that was pi radians, and you can simplify that. So whatever the 75 pi over 180 reduces to, and this would be in radians. So this 75, 5 goes into each of these, obviously. 5 into 75, I believe that's 15. And 5 into 180, I think it's 36. So 15 over 36, each of those are divisible by 3. 5 over 12 radians, if I didn't do that too quickly and make a mistake. Next one. NASA's tracking a satellite traveling in a circular orbit above the Earth, only tracked when its orbit is pi over 6 radians. So I've got my pi over 6 radians, and then this total length here for the radius of the orbit. If you take the Earth's radius and then add on how far it is above the equator, you're going to get for those two your total radius of the orbit out here to be, what's that, 6720 kilometers. And so if it's asking for what's the length of this arc right here, remember we had a radian equaled the arc length over the radius. We talked about that earlier on a little example. So if the radian is pi over 6 equals the arc length over the radius, 6720 kilometers, and I want to solve for the arc length, we'll just multiply by the 6720. And if I do that, it'll simplify there. 6720 kilometers. Divide that by the 6. I believe it divides evenly. 6720 divided by 6. And you get 3519 pi, because the pi is still there. And so 30. So when you multiply that all out, the answer is about 3519. So that's going to be kilometers. Right, that's the same one. That's the one I just did. All right. Oh, that just has the try it in it. And hopefully that summarizes the lesson. So you've got your terminal side, rotate positive, rotate negative. You can also do the rotate where it's more than 360, and they all end at that stop. We always start here at the initial side. And then our radians, that's pi radians over here, and it's 180 degrees. And if you went all the way around to 360, that would be 2 pi radians. And so that's why you see this right here as what I would use for my conversion factors. And then we always have just 3 standard ones that we work with. We've got this 30-degree angle, we've got a 45-degree angle in here, we've got a 60-degree angle up there, and then those are in every one of the quadrants. And we'll be working with those more later on. So that wraps up that lesson. I hope that gives you a bit of an idea for a summary of that 7-2 introductory lesson to radians.